Hey everyone, so today we're going to continue on chapter 9 of Steck's electronics book. This section is going to be on 4.9 on bias network, which is a modification to the common emitter amplifier that we talked about just before at the end of the last lecture. And we'll also talk about some the Apromol model. Do I do something? Oh no, we also talk about the differential amplifier before that. And I think that's all we will have time to cover in this class at least. I will note at the end that there's going to be there's a lot more information on this chapter than what we are covering, but it's just due to lack of time that we won't be able to cover everything in here. So if you're interested in more detail about how transistor work and how to deal with this temperature dependent beta factor, and how there's other transistors, the field effect transistor, which is actually how modern day processors and memories are made. I really suggest that you keep reading on this chapter and also read chapter 5, which is going to be focused on the field effect transistor. Okay. But for now, let's talk about the bias network. So the book also called an AC coupled amplifier. I usually learn them as just a amplifier that has pull-up resistors, which actually what it sounds like, because it pulls the voltage up so that you're not amplifying the negative. Well, you're amplifying the negative input, but you're pulling it up so that the negative swing is still positive. And we'll see how that turns out. Okay. So why do we need something like this? So oftentimes AC signal, I'm going to draw it down here, right, has a positive and a negative swing. Let's do it here. There's a lot of space on the right here. Okay, right. So you have some VN, that's swinging positive and negative. Okay. What you find is that on our amplifier, right, we have a VCC, but then the lower end of the emitter side of the transistor is actually tied to ground. So that means all of this actually gets cut off. It's actually known as clipping. So what we want to do is actually move the signal up so it's always positive, so that this clipping effect no longer affects us. So we have to figure out how much to pull this up, right? And this is essentially what the circuit allows us to do, and this will be the circuit you'll be building a lab to investigate how this works. Okay, let's see, go back to red. Okay, so as I noted, the common emitter amplifier that we just studied before cannot deal with negative voltage inputs. Okay, this is where bias network comes in. I also call them pull-up resistor, as I mentioned. And the idea is that we're going to pull up the input by this bias point. So I call it pull-up. The book calls it bias point. So different people call it different things. And this bias point is going to be pulled up by this VCC voltage times a voltage divider factor of R2 over R1 plus R2. And you can really just see this here pretty quickly. Okay, so I'm going to start highlighting. So this is the normal common emitter amplifier part. And over here in yellow, right, you basically have a voltage divider, right, before the input into the base of the transistor. Okay, you're basically, whatever AC signal you're sending in, you're adding this amount of voltage to it, which is a DC voltage, so that you pull up the signal so that you don't have a negative swing in your amplifier anymore. Sorry, in your input anymore. Okay. Of course, there's going to be this capacitor there. The reason that capacitor has to be there is basically to isolate VN from VCC, because what's going to happen if that was not there, if VN is lower than VCC, then the current actually flows from VCC into your VN. If VN is bigger than your VCC, which is hopefully not the case, current actually flows the other way, which you don't want. Okay. So the fact that you added this capacitor has the effect, and we're going to talk about what that is. Okay. The gain of the amplifier does not change because the screen part did not change at all. We still have the gain being the ratio between the collector resistor divided by the emitter resistor, and this is always going to be an inverting amplifier. Therefore, the signal will get flipped upside down. Okay. The capacitor at the input is to prevent the potential DC offset from getting into the transistor base, and also protecting this VN and VCC. So it does, by adding a capacitor there, it does remove some low frequency signal from your amplifiers. So if we use Thevenin's equivalent, we can combine R1 and R2 into a Thevenin's equivalent. Okay, and this is essentially your R Thevenin is just R1 parallel to R2. Okay, and then that output goes into the transistor. Okay, so but the transistor's input impedance, remember, is just RE times beta, because beta amplifies is the application of the current, and if the current gets amplified by a factor of 100, then the input impedance of your transistor amplifies that by a factor of 100 also. So that's also in parallel. So basically, if you want to calculate the F3 dB point of a, let's go back just to make sure that we're okay. If you want to calculate F3 dB of a RC circuit, right, you have F3 dB. You always have a 2 pi because of the F, right, over RC. Okay. But in this case, instead of having R, we have basically R parallel to R1 parallel to R2 parallel to RE times beta. Okay, where beta is the factor of 100 you get from the transistor. So essentially, the F3 dB point of this amplifier with the pull up and the capacitor in there is going to be 1 over 2 pi times all these parallel resistors value times the capacitor value, of course. Okay. Okay, so let's look at the book's example where we set VCC at 15, R1 is 56, R2 is at 5.6, the capacitor value is 100 nanofarad, and then RE and RC gives you a gain of 10x. Okay, if you plug these numbers in, turns out that this F3 dB is going to be about 300 hertz. Okay, so that means this common emitter amplifier works well if you're sending in signal above a kilohertz. Okay, but if you go down to about 300 hertz, it will start actually not amplifying your signal. Okay, so actually both amplifies it and also filter it out because you're passing it through a low pass filter. Sorry, a high pass filter. Okay, so notice that in this F3 dB equation, it has this beta value in it, which can cause a problem because notice that we should not count on beta being a constant, right? As you run the transistor, beta actually changes because the transistor will heat up. Okay, so most of the time what you want to do is actually keep beta, beta times RE to be much bigger than R1 parallel to R2, and therefore you're mitigating most of the impedance, most of the current flows through R1 and R2 instead of through beta times RE. Okay, right. If we plug in the equation for the bias point, okay, plug in this voltage divider, this bias point is actually going to be 1.63 volt. Okay, that means whatever signal you send in is going to get shifted up by 1.36 volts. So if you send in something that's negative 1.5, it will still have a negative swing. So you want to kind of keep this plus or minus 1 volt on your signal input, and therefore this pull up resistor allows you to make it positive, and then the application occurs, and then you're not having to deal with clipping, which where the amplifier is not actually able to output voltages that you want it to. Okay. So yeah, so this will shift the signal up by 1.6 volts. Let's go back to red. Okay. And since the gain of the amplifier is 10x, that means, right, this, since your signal cannot be bigger than 1.36 volts, and you're multiplying that by 10, the output will actually be somewhere between positive, well, the output will only get amplified, this is actually not correct, up to positive 13.6 volts, and then the bottom is actually 0, so you cannot have anything that's going to be less than 0 as output. Okay. The clipping issue we talked about, right, is that the maximum output of the amplifier is determined by the VCC voltage, which is going to be set at 15 volts. And then minimum actually is the diode voltage, because if you have anything a bit less than the diode voltage, you actually cannot output that anyway. Okay. So any signal beyond this, this signal times 10, so you have to take care of this times 10, right? It's beyond the range of your amplifier, and the signal will get clipped. And this range, this input range, right, is going to be what's known as the dynamic range of your amplifier. Okay, so this is the bias network. Let's call it that. I call them just the pull-up resistor common emitter amplifier. So that will allow us to offset all your inputs so that you don't you're not getting a negative part of the input, so that you're not trying to amplify a signal that you cannot output. Another way around this is actually tie the negative end of your amplifier, right, RE, right, to VEE instead, which could be, you know, down to negative 15 volts if you want, right, 15 volts. So that's another way around it. If and we do have these negative output power supply available in the lab. Okay. All right. So I'll talk about next. 12 minutes. Okay. I'm just keeping track of the time. Let's talk about the transistor type of differential amplifier. I'm going to go through this much quicker. We're not going to have a chance to build this in the lab because it's really hard to see the effect, but it's important amplifier for you to know, because oftentimes this is the amplifier that actually people use as opposed to the common emitter amplifier. Okay, let's look at this circuit diagram real quick. So on the left hand side here, you have a common emitter amplifier here, right? You have a transistor, you have some resistor at the collector, at the emitter, you have some input. We're going to call that V1 instead of VB because we're going to have two inputs. Okay, on the right hand side, right, we have another common emitter amplifier, and what I would call ground, right, what used to be ground, right, in the single common emitter amplifier case, we're going to call that point A, and that's going to be an important point because that's going to be actually kind of like your virtual ground that your input's going to be compared to in order to get a differential amplification. So so the main idea of this circuit is that it amplifies the difference between the two signals, but then it knocks out the sameness between them. So if your signal, let's see, let's do a little drawing here so that I can illustrate this. Okay. Yeah, so this is VEE, so we can have a negative output, right? Let's say you have a signal like this, and it's going up and down, right? But it has some noise in it. Let's make the noise blue, right? A little hair here, right? So the amplifier is going to pick up these noise and amplify that noise also. Okay. What the common mode allows you to do is that if you have two different lines, right, that are sending equal and opposite signal to each other. So let's say one goes up, the other one goes down. Let's do that green, right? So this is going to be, say the green is V2, the red is V1, right? And there's still noise on top of this, right? But the noise is common between the two of them. And a lot of times that's going to happen because if the wires are in the same environment, they'll pick up the same noise from the environment. For example, in our room, there's going to be the 60 hertz noise that's happening all the time because all of our AC outlets are on 60 hertz. So you're going to see the 60 hertz noise all the time. So that's a common mode noise that can be knocked out by this. Okay. In a circuit diagram, a lot of the time what you're gonna see, instead of seeing this complicated circuit, is they just change it into a triangle, and then you have a V in plus, V in minus, and you have a single output. And the single output is designed so that it amplifies the difference between the two inputs, and that's all I care about. And we're gonna see that this is actually going to be in the future known as operational amplifier, where this A, instead of being, 10, 20, 1,000 or something like that, is going to be like maybe like 1,000,000. And we'll see how that turns out. Okay. And how we can actually apply that. Okay. So I'm not going to go through the calculation in too much detail, but I just want you to see how it works. Okay. So the techniques you analyze this with is that you basically split the two input signal that you're feeding into both sides of this, okay, into the difference between them, okay, which is signified by delta V, the difference between them, and what's common between them, which is this bar, which is the average. So V bar is the average between the two signals. So this is the common part of it. Delta V is the difference between the two signals. And we're going to see how this amplifier treats this difference versus the common. And the way we do this is by just thinking about it in terms that, if we only have difference, how does the amplifier behave? If we only feed it into the common, meaning the average voltage, how does the amplifier behave? So we're going to do the difference first, because that's actually the part that's important. Okay, so if we're only dealing with the difference, what we're going to do is going to set V2 and V1 to be just delta V over 2. And then V2 is minus delta V over 2 because of this minus sign between them, right? It's the negative part. Okay. All right, in this case, right, the voltage, the AC part of the voltage at the emitter, right, this is going to be the voltage at the emitter 1, and this is a lowercase. It's going to be equal to the voltage at the base, and it's once again the lowercase version of it, the AC part. So those are all the same, because once again, remember when we're dealing with AC and DC, we just drop the DC part because the amplifier actually does not pick that up. Okay. Similarly, right, V2 is going to be equal to VE2. So we know the voltages at these 2 points is going to be equal to the input voltages on the AC part. Okay. What's kind of neat about this is that, well, if you look at this, right, this used to just tie to ground, this point A here, right? In this case, it just turns that what used to be ground to be a voltage divider between the two emitter resistor, right? And since if we make these emitter resistor to be the same between the two sides, what's going to happen is that the voltage at A is just going to be the average between the two emitter voltage, right? And since we have V1 plus V2, and remember, right, in this case, we're only dealing with the difference. I don't know why the book just doesn't fill in the last part of this algebra, right? So it's just delta V over 2 all divided by 2, plus negative delta V over 2, right? All of this subtract to 0, ideally, okay? Okay, so this is sort of interesting. It basically forces this point A to be kind of like a virtual ground between the difference between the two amplifiers, which is actually kind of a neat thing that you can do this with the just resistors. Okay, and the main thing is that, well, if V1 goes up by one amount and then V2 goes up by that same amount, what happens is that both of those go up together, and VA actually goes up by the same amount, and that makes it still the same ground. Okay, and this is why it is removing the common mode voltage changes that you may see. Okay, so this amplifier only amplifies difference between V1 and V2. So the V out is actually going to be RC over RE, but with this extra factor of 2, because you have this little voltage divider situation with the two REs, right? Instead of one of them going to ground, you have the voltage divider going to ground. And it is only amplifying the difference between V1 and V2. And the gain of this is, of course, going to be negative once again, which is negative RC over 2RE. Okay. For the common mode, so there's about a page of algebra on this also. I'm just going to give you the result because I just want to kind of show you guys the next important concept real quick. The common mode, we can go through the same analysis, but instead of plugging in delta V, you plug in V bar instead, right? Because that's the common mode part. We go up here, right? Here, right? This is the common mode. This is the difference, right? Okay. So we plug that in, and what you'll get as the gain, common mode gain, is just going to be RC divided by 2RE plus, RE plus 2R double E, which is the last resistor before you go to the negative voltage supply. Okay. One thing I want to show you guys is how people quantify how good your differential amplifier is. And there's a very simple equation to do that, and that's the cool thing about it. Okay, this is known as common mode rejection ratio. And it's basically the ratio between the gain of your differential mode divided by the gain of your common mode. Okay, all right, if we plug that in there, the factor of RC actually disappears, and what you end up with is the common mode rejection ratio is actually RE plus 2 times RE divided by 2 regular RE. Okay, and typically what you want to do is design amplifiers so that this R double E, right, is much bigger, maybe a factor of 100, maybe even 1,000, to make it so that that you can actually simplify this common mode rejection ratio to be just the ratio between the big REs, so the R double E's, divided by the R single E. And this is how you actually quantify a differential amplifier. So the bigger that number is, the better it is at differentiating common mode signal and rejecting the common mode signal noise. Okay, so 23. Okay, trying to keep this short, around 30 minutes. So what I'm going to do is I'm going to go through one more section in chapter 4, which is the Ebert-Moll model of transistor. So up until now, right, I just been telling you that this beta factor, right, is there because, right, in the case of the NPN type of transistors, right, where the P type is lightly doped and thin, right, I haven't really quantified it, right, just thought, oh, it's light and thin, therefore most of the current, right, travels from the collector to the emitter, and only a small amount travels from the base to the emitter, right? And that ratio gives you this beta factor. Okay. I also noted that this beta factor depends on temperature, but I didn't explain why. So what we're going to do, we can actually explain this if we go back to the diode law from chapter 3 and use the Eber-Mole model in order to see how the current behaves near the diode voltage point around the depletion zone. Okay, so remember that the diode law from chapter 3 is that the current that you get is equal to some saturated current, and this saturated current is usually very small, meaning it's the current that occur when you don't bias it. You just have kind of when you reverse bias it, you just have some random holes opening up and some free electrons moving around. And so the thinner the p-type semiconductor is, the smaller this saturation current will be. But you don't want that to be 0, because otherwise you don't get a transistor, or actually in this case just a diode. Okay, and that's going to be, and this current gets amplified exponentially if you put a voltage across it, right, where V is the voltage across that diode, and then N is this idealization factor between 1 and 2, right? Okay. And then Vt is this thermodynamic term, which is K Boltzmann's time, the temperature in Kelvin divided by the charge of an electron. Okay, at room temperature, this is about 1/40th of a volt. This thermal voltage. Okay, so we can use this model basically with Eber or Mole just stole this. Well, maybe they came up with this, came with this equation, and just use it to quantify how does the current traveling between the collector and the emitter behaves as a function of the voltage drop across those diodes. Okay, so this is the Ebers-Mole's equation. Hopefully it looks very familiar to this, right? We're just applying this to the collector part of your transistor. Okay, this book, also note that this is known as a transconductance device, which is sort of a new term that I don't remember seeing previously. The reason it's called that is because trans means change, and conductance means making current, right? So this little equation basically tells you how a voltage difference gives you some current. In the future, we're going to have transimpedance devices, where instead of converting voltage into current, you actually convert current into voltage. So hopefully that's not too strange to see. Okay, so let's make the idealization where let's just make n equals to 1, and then we just drop this factor of -1 here, because we're going to know that, VBE is going to be much bigger than VT, so this exponential is going to be a large number, so we can ignore that 1 at the end there. In fact, the book gives us some numbers, so VT, as usual, is about 1/40th of a volt, or more accurately, 26 millivolts, okay, at room temperature. So we have to plug this number in Kelvin. The voltage across the diode is 0.6 volt, right? If you look up the saturation current for this 2N4401, which is the device that the book used, and I'll have you look up a different one when we're doing the pre-lab, right? You have a saturation current of about 2 picoamps. So if you do this calculation, you're going to find that the collector current is actually about 25 milliamps, so which is, some substantial amount of current. It's not nothing. Okay, but the main point is that it's going to be much bigger than the saturation current because of this ratio of 0.6 divided by 0.026, right? Because that's going to be this exponential is going to be a number that's on the order of maybe 20. So e to the 20 is a pretty big number. Okay. All right, to get IB so that gives us the collector current, right? because the main point is that we want to get to a way to figure out what how the collector current depends on temperature, but then now we need to get to the base current, which is the current between the base and the emitter. Okay, to get to the base current, we do the Ebers-Moll equation again, but instead of solving for IB, what we're going to do is we're going to invert this equation so that we can get to the voltage between the base and the emitter. Okay. Once again, if we just take n equals to 1 and we're ignoring these factors of ones everywhere, what we get, assuming that this ratio is large, right? What we get by plugging it back into equation 4.61 is that the collector current is amplified proportionally to the base current by this factor of the saturation current. So IS is the sat current from the collector to emitter, right? And then ISE, just yeah, it's just so funny how they, I mean, I could have put a C here, right? It's the same thing, saturation current from the base to the emitter instead. Okay, and this ratio between them is actually what beta is. Okay, so this kind of gives us kind of a microscopic view on what's going on here, right? So hopefully it physically makes sense without these equations. But what's happening is that when you have some small amount of current that allows these free electrons to get into the depletion zone, you know, some saturation current flows, some saturation electron flows into the base. In other words, the regular current flows out of the base into the emitter, right? Where majority, right, meaning like a factor of 100, is actually flowing from, of the current is actually flowing, of the electrons are flowing in from the emitter into the collector. In other words, right, using the sign convention of positive charge as the current, we have a much larger current from the collector and then a much smaller current from the base. So hopefully that's helpful for us to understand how the thermodynamics of these electrons moving around kind of gives us the this beta factor that we've been using all this time, and we just kind of said that, oh, that's the case because we made the transistor that way. Okay, so that's all I'm going to cover this chapter. So I do want to note, a little bit over time already, right, that this chapter has a lot more stuff in it that's really neat. There are other circuits in it that's useful, particularly like there's a circuit called the Drill Thief, which allows you to make a little flashlight that you can use when the voltage on your battery runs too low for it to power it up. You can actually use that to actually amplify the voltage on and off, so you actually get you get a flashlight, but then it's flashing so fast that it makes for a human it looks like constant. There are more models and more details on how the current and the beta function depends on temperature. So if you're really interested in investigating getting into semiconductor work in the future, or just investigating how material behave when you sandwich different dope materials together, definitely suggest you read through those sections. And if you have any questions, please ask me. I'm really, it's just because we're out of time. I don't want to make the lecture 2 hours long, and that's why we have to stop here. Okay.